Good day to you, viewers. Today, we want to have a look at the topic calculus. It's going to be in stages. Calculus is divided into two parts: differentiation and anti-differentiation, which is also called integration. But we are starting with differentiation, and we are starting from the grassroots, which is the beginning of calculus, which is the genesis of calculus, and that is calculus from the first principle. First principle is developed based on the understanding of the gradient of a line. So we are going to use the knowledge of gradient to establish first principle. Let us consider a curve. This time around, it's a curve. It's not a straight line. And let the curve be y equals x squared. That is, y is a function of x, meaning y depends on x. Y will be interpreted as dependent variable, while x is the independent variable. Having sketched the curve of y equals to x squared, look at the curve. Then let's consider a point P on the curve. So I'm picking a point P here. And every point on the xy plane, this is y-axis, this is x-axis. That's what we call xy plane. Every point on the xy plane has a coordinate. That is, the value on the x-axis and the value on the y-axis, the abscissa and the ordinate. So when I drop down a dotted line on the x-axis, let's say from here, from the origin to this point, where point P is dropped to the x-axis, is x. That is, the gap from the origin to here is x. Then, from here to here will be the value of y, as indicated here. From here to here is y. Y from here to here is x. Now, then let us now assume that there is another neighboring point Q, which is here. Point Q also will have its own coordinate, but it is obvious that point Q is higher up in position than point P. That means the value for the x-axis for the point Q cannot be x again. The value of x must have increased. So I am using this notation, delta x, to represent increment in x. This symbol is called delta. Delta. So that's the symbol. Now, but delta x is a single entity. It simply means increment in x. So definitely once the value of x has increased by delta x, value of y also must have increased by delta y, which is this. Now, from here to here is the increment in y, which is delta y. Now, having done this, if I want to find the gradient, do not forget that the basis of gradient is increment in y over increment in x. So let's have a look at this now. That means that y, which is equal to x squared, has undergone increment as a result of increment in x. Then y is no longer y, it's now y plus delta y. That is y plus the increment in y equals to what happens to this side also? That will be x plus delta x, then raised to power 2. Because this x is no longer x, it has increased by delta x. So bracket, then the square on the function given is here. Now, let us transfer y to the other side and leave delta y, because it is from the idea of delta y that we are going to get the gradient. Delta y will be x plus delta x all squared minus y. But do not forget that y is equal to what? X squared. So I'm going to use x squared to replace y here. While I'm going to expand this, you can be doing the expansion on your own. Delta y equals x squared plus 2x delta x plus delta x all squared minus, instead of writing y now, I am going to replace y with this x squared, because y equals to x squared. That is the initial function given. That is the original function given. It is obvious that this will cancel out this. Now we have delta y equals 2x delta x plus delta x all squared left. Then what do? Let's divide throughout by delta x to achieve the word gradient. Dividing throughout by delta x. Then this delta x will cancel this one. We have 2x left here. Plus this delta x will cancel one of these. We have one delta x left. Now, what we have left here is delta y over delta x equals 2x plus delta x. Now, we want to talk about the limiting value of this. What do we mean by limiting value? As we saw in the sketch, that Q is above point P on the curve. So let's now assume that we are bringing Q down. We are drawing it down. This P here, this Q here. Let's say that we are moving Q down towards P. As Q is moving towards P, what is happening to delta x? Will it be increasing or decreasing? It will be decreasing. And that means delta x can be said to be approaching 0. Not that it is 0, but is approaching what? 0. Because the moment delta x becomes 0, then we are already back at P. And we want to be close to P no matter how. That means that as we are decreasing, as we are moving down point Q towards P, delta x is approaching 0. So as delta x is approaching 0, then delta y over delta x will be approaching its limiting value, which is the gradient function of the curve. Now, as delta x tends to 0, we use this arrow to show that delta x is approaching 0 or tends to 0. As delta x is tending to 0, is approaching 0, then delta y over delta x will be approaching its limiting value, which is dy over dx. And dy dx is called gradient. Now, so what does that mean? It means that for this to become this, which is the limiting value, that is the limit of this, it means that anywhere we see delta x, we use 0 to replace it. Therefore, dy over dx will be equals to 2x plus 0, because 0 will be replacing this delta x. And, of course, what is the answer? 2x. Now, 2x is the gradient function, which is also the limiting value for the curve y equals to x squared. So, this approach is what we call first principle. We use it in differentiating a given function. If you are asked to differentiate from the first principle, this is the approach you are expected to use. So starting from here, with this understanding, we can now end the first part of this lecture. In the next few minutes, we'll resume to apply first principle in differentiating a given function of x.